So now let's look at a recap on power and Taylor polynomials. So here's a recap of power series, which are power series and Taylor polynomials. So here's a quick recap of power series, which are a specific type of series. So power series looks like this. You have a coefficients in front, and summation from n equals 0 to infinity, and then you'll have x to the power of n. So you're going to have it go like this. It's going to be coefficient at c0, then c1 times x, c2 times x squared, plus c3 times x cubed, and so on. And keeps going on. And power series centered at a, this is more general one, so you, instead of just x, you'll have x minus a, like that, inside every single term there. And the convention over here, x minus a to power of 0 is equal to 1 is used, even when x is equal to a, so you have a 0, it's going to be a minus a is 0 to power of 0, so even in that case, we're going to use it equals to 1. And recap the theorem in my earlier videos. So for a given power series like this general one here, there are only 3 possibilities. A series converges only when x equals to 0, because remember you just plug in x equals a. If you plug in x equals a, all of these vanish. You're just left with this first term. So that's one possibility. Or the series converges for all values of x. Or there is a positive number r, called the radius of convergence, such that the series converges if absolute value of x minus a is less than r, and diverges if absolute value of x minus a is greater than r. So again, note that r is a radius of convergence, and in the first case right here, r is equal to a for I, and r equals to infinity for I, so it goes to infinity there, for all values of x. And also note, so when absolute value of x minus a is equal to r, then a series may converge or may diverge at the endpoints of the interval of convergence. X equals to a plus or minus r. So in other words, at the endpoints, which is this point right here, or actually just reword it a bit better, just moved it around. So when absolute value of x minus a is equal to r, i.e. at the endpoints of the interval of convergence of at the endpoints x equals a plus or minus r, then the series may converge or may diverge. So here's how it looks like this. So a, it always converges, and then at a minus r or a plus r, at these points it may or may not. So we have an open circle there. So may or may not, but inside, so you could have it converge over here. Absolute value of x minus a is less than r, and then outside would be divergent around there, depending on what r is. So anyways, going further. Recall that the Taylor series is just a power series in which the coefficients are determined from the function's derivatives. So recall from our earlier video on infinite sequences and series, Taylor and Maclaurin series. So theorem, if f has a power series representation or expansion at a, that is, if f of x is equal to this power series, the general one like that we were given, or that we just went over earlier, then its coefficients are given by the formula. So you could get the coefficient Cn equal to the nth derivative at a divided by n factorial. Then if you expand this all out, you'll have f of a plus f prime of a divided by 1, and then times x minus a. Then the second derivative at a divided by 2 factorial times x minus a all squared, and then the third one, and so on. And the Maclaurin series is just a specific type of Taylor series with a equals 0. So plug in a equals 0, so all you have is this x. So you're just going to get this series like this: f of x equals 2. The summation from n equals 0 to infinity of the nth derivative at 0 divided by n factorial times x to the power of n. So you'll have f of 0 plus f prime of 0 divided by 1 factorial times x plus f double prime at 0 of divided by 2 factorial times x squared plus etc. Keeps going on. And a function is equal to its Taylor series when the remainder approaches 0. So if you have f of x equals to the Taylor series plus a remainder, so the error, in it where t sub n is the nth degree Taylor polynomial of f at a, and you have the limit as this remainder term goes to 0 as n goes to infinity for the radius of convergence for absolute value of x minus a is less than r. Then f is equal to the sum of its Taylor series on this interval, absolute value of x minus a is less than r. And also Taylor's inequality is used to evaluate the remainder. And Taylor's inequality, again, recall from an earlier video. So if you have f, if you have the absolute value of the n plus 1 derivative is less than or equal to a number capital M, for absolute value of x minus a is less than or equal to d, the radius of convergence, then the remainder r sub n of x of the Taylor series satisfies the inequality. So you have the remainder, the absolute value of the remainder is going to be less than or equal to capital M divided by n plus 1 factorial times x minus a, absolute value of x minus a to the power of n plus 1 for this radius of convergence. We have d there because we're using the remainder for r. So for x minus a, absolute value is less than or equal to d. Now here are several common functions in their Maclaurin series, and I'll be referencing these throughout the video, so it'll be pretty interesting stuff. So this is ones that I covered earlier. And this one here is the binomial series, which we'll use a lot. Yeah, I was surprised at how much it's used, especially in physics.